So last time I was talking about H vectors of simplicial polytopes, which, by the way, why simplicial? Why not arbitrary polytopes? Like, for example, let's say I compute some H vector of a non-simplicial polytope. Maybe I try, let's say, a square pyramid. If you remember, we had this weird triangle procedure. So, right, F0, F1, F2, right, something like this, 1, 1. So F0 in this case is 5, and F1 is 8, and then F2 is 5. So if I start subtracting, then what I get is -2, 6, not symmetric, not positive. Very bad. I mean, the whole picture just doesn't work for non-simplicial polytopes. So yeah, H vectors are very special to simplicial polytopes. Yeah, that's a good question. I don't know. I wonder how you would prove it. That's interesting. Yeah, probably there's some coincidental large polytope which has somehow still non-negative. Yeah, maybe we can try to come up with an example. Yeah, it has to be a three-dimensional example because for 2 dimensions, every polytope is simplicial. But anyway, yeah, that's a good question. And but there was another question, which is like for dual polytopes, can you force the vertices of the dual to be in the facets of the original one? And I Googled it. I think it's an open problem. Not exactly sure, but it looks like, yeah, it looks like this is an old open problem. All right. So today we're going to study another super nice polytope, which is called the associahedron. What is the associahedron? Well, let me remind you, as you all probably know, if you take an n+2 gon, and so you take an n+2 gon, and then you want to subdivide it into triangles. Number of triangulations of an n+2 gon is, so by triangulation here, I'm going to mean that I'm not allowed to introduce any vertices in the interior. So only using the vertices of your original polygon. So what is this number? The nth Catalan number. Thank you. Cn, 1 over n+1, 2n, choose n. That's the Catalan number. Very nice numbers, super important in all of combinatorics. So, okay, now let's say if I want to draw some triangulations, maybe triangulations of the square, there's 2 of them, right? Triangulations of the pentagon, they're all basically rotations of this one. So there's 5 of them, and etc. So I'd like to have more structure on these triangulations. I mean, counting them is nice, but what else can you do? And so here is a definition which is originally due to Tamari in 51, later Stashev in 63. Yeah, so it's called, the associahedron is called the Stashev polytope, even though Samari was the first. And so here's what I'm going to do is I'm going to do slightly weird thing. I'm going to define not a polytope, but a phase lattice of something that's hopefully a polytope. I'm just going to define a lattice, or even just a poset. Phase lattice of the associahedron. I guess I'm going to know the associahedron sub n is the poset. Instead of taking just triangulations, I'm going to take all subdivisions of an n-gon into using some of the non-crossing diagonals. Poset of subdivisions of an n plus 2 gon using diagonals. Well, into polygons, by diagonals. And what is the, I mean, if it's a poset, there should be an order relation. So my order relation is going to be just inclusion or refinement or whatever. Ordered by refinement. And by refinement, I mean just keep adding more diagonals. Yeah, and so maybe I should try an example. Yeah, let me add let me add one extra, the empty phase to this poset. With extra minimal element. The empty set is going to be the minimal element of my poset. For example, let's say I take the square. So here you have to choose whether triangulations are like the minimal elements or the maximal elements. So I want I want my refinement to go down. Triangulations are minimal here, other than this super minimal element. Anyways, let me draw an example. So you have the square, you have two triangulations, and then there is the minimal element, and then there is a subdivision of the square into a square. That is the phase lattice of the associahedron sub 2. Is this the phase lattice of a polytope? Yes. Which one? The square. Ah. Hmm? Yeah, a segment. Okay, nice. Yeah, if you take a line segment, then you can label the vertices by triangulations, and then the one-dimensional phase by just the empty square. So you get, and then the empty set is the empty phase. All right. Now, if I try to do the same for, yeah. Yeah, let me say reverse refinement. I mean, it's because we know about duals of polytopes. It doesn't really. If I want to define a phase lattice, I can yeah. And some people actually think of triangulation as maximal elements. That's going to be, to me, that's going to be the dual associahedron. Anyways, I want the vertices of my associahedron to be labeled by triangulation. Okay. If this is n equals to 2, if you try n equals to 3, it's a little bit tiring. So there is the empty set, and then there is a triangulation, and then there is another triangulation, maybe like this, and then you keep going, and then these two have a common diagonal. This. I can do one more. And then there is the empty pentagon on top. So there is 5 triangulations here, and then there's 5 diagonals here, and then there's 1 pentagon. So is this the face lattice of a polytope? Yes. Which one? A pentagon. Okay. So that's the confusing coincidence, but this associahedron sub 3 is a pentagon whose vertices are labeled by triangulations of the pentagon. And so basically, that definition tells you that I want a polytope whose vertices are labeled by triangulations and whose edges are labeled by triangulations that share all but one diagonal. Whenever we have a triangulation of some nice polygon, if you pick one diagonal and you remove it, then you get a quadrilateral, so there is a unique other diagonal you can add. So the previous one and then this one form an edge. Edges correspond to flips of diagonals. Yeah, and of course, I mean, I want such a polytope, but it doesn't mean that it exists. High dimensions, it has some, you have to make sure, like, given a triangulation, how do you put it, how do you associate a point in some high dimensional space to it that would actually make sure that, whenever you see a small, let's say you have a giant triangulation like this, you have a giant subdivision of some polygon. Yeah, and maybe there is a small pentagon here. Then you have to make sure that all of these 5 triangulations of this pentagon have to lie in the same 2-dimensional plane of your high dimension. Yeah, so it's a tricky problem. And in fact, it was open for like 20 or 30 years. So yeah, so the main question here is there polytope with this face lattice? And the answer turns out to be yes. So after 20 to 30 years, depending on which date you think is the origin of the associahedron, some realizations were constructed. So here, I'm solving a different problem. I have a combinatorial type of a polytope, and I'm trying to find a realization, trying to put it in d dimension. So, and it turns out that there's not just one canonical realization, but there's many different, very different triangulations. Say again. So, I mean, I think both of these people made this conjecture. So Stashev actually constructed it as some curvilinear subset of n-dimensional space. And he was motivated by some kind of homological consideration. He was doing topology at the time. Yeah, I think it was a conjecture in this paper. Yeah, I don't know if he actually mentioned it, but so basically, if you try to draw this is the 2-dimensional associahedron. If you try to draw the 3-dimensional one, it's very suggestive that it looks like a polytope. I mean, I should have brought some pictures for you guys, but it's a polytope with like 14 vertices in 3-dimensional space, and it looks like there's no coincidence that it should be always a polytope. But yeah, of course, proven that. So this conjecture is very natural as well, by looking at 3-dimensional examples. Yeah, and so many different realizations. And I'm going to tell you about some of them. I know like 4, maybe, I don't know if I tell you all 4 or maybe like 2 of the 4, but there's many. And some are better than the others to me, but they're all sort of, there's no canonical one. And before I talk about realizations, let me mention a few names. The first one was Hyman in 84, and this is an unpublished preprint. And then there was Lee in 89, and then it's just the list keeps growing and growing and growing. There is realizations coming from cluster algebras by Fomin and Zelinsky, and then there's secondary polytopes of Gelfand, Kapranov, Zelinsky, and a few more. Anyways, before I go on, let me mention just, let's assume this polytope exists. If exists, what are the properties? Is it simple or simplitional, or neither, or both? Okay, so in 3D we have pentagonal faces, so definitely not simplitional. That's good. Is it simple? Hmm? Yes. Why yes? Cool. Okay, right. So if, yeah, the edges should correspond to flips of the diagonals. So if you have a triangulation, you have n minus 1 diagonals, and therefore you can flip any of these. That's gonna, so the degree of each vertex is gonna be, or n diagonals, is it n minus 1 diagonals. So yeah, first of all, what is the dimension? What is the dimension of the associahedron? It should be n minus 1. Yeah, we don't know why, but based on these examples, should be n minus 1. I mean, we know why. So it is simple since each vertex has degree n minus 1. And yeah, anyways, you actually know the dimension because if this is a 0-dimensional face and has n minus 1 diagonals, then this is going to be a 1-dimensional face and 2-dimensional. Like this poset is what is called graded. There's levels. It's graded by the number of diagonals. In particular, if this is 0-dimensional, this has to be n minus 1 dimension. All right. Simple. So in particular, because it is simple, the dual is simplitional. And before we actually construct realizations, let's see what happens for the dual. If we compute the f vector or the h vector, and we're not going to actually compute it, but let me just tell you what is the f vector. The f vector of the associahedron, of the dual associahedron, because we want the h vector to be non-negative and symmetric, it's given by some formula. F sub j minus 1 is 1 over n plus 1 times n minus 1 choose j times n plus 1 plus j choose j plus 1 for j from 0 to n minus 1. So let's maybe check this in an example. Let's say I take n equals to 3. Then my formula becomes f sub j minus 1 is equal to 1 over 4 times 2 choose j times 4 plus j choose j plus 1. And so if j is 0, I should get f sub -1 is 1/4 times 1 times, which is 1. That's good. And if j is equal to 1, then f sub 0 is what? 1/4 times 2 times, yeah? Right, so the wait, hold on. So the dimension is n-1, right? And so this defines f sub n-2, right? So if you plug in j equals to n, you get 0 here. So it's right. It's an exception of this formula. But it's actually good for us because if you remember to define the h vector, you don't need the last. All right, so 2 times, what is it? 5 choose 2. Oh, 2 choose 0 is 1. Okay. What? No, 2 choose 1. That's 2. The next one is 5 choose 2, which is 10. You get 5. That's good. That's the number of vertices of the pentagon. That's pretty good. Yeah, so this formula works. F sub 1 is 1/4 times 1 times 6 choose 3. Well, yeah, 6 choose 3, which is 20. So you get 5 as well. Yeah, so that's the pentagon. And works in general, and maybe it's going to be in the, yeah, by the way, I should put up a homework over the weekend or so. There's going to be homework. Maybe, yeah, some problems out of the ones I mentioned are going to be in the homework. So yeah, anyways, that's the f vector. In particular, if you count so what is the Catalan number? The n is the number of vertices of the associahedron, so it's the number of facets of the dual. And indeed, so if you want to compute facets, then you need to put j to be n-1. And if you plug in j equal to n-1 in this formula, this becomes 1. One over n plus 1 times 1 times 2n choose n. So it works. All right. But so any questions on this? Anyways, this works, but yeah, of course, what we know from the previous lecture is that the f vector is not really the special one. Special one should be the h vector because it's simplicial. So what is the h vector? H vector of the dual associahedron is given by, so hi is 1 over n times n choose I times n choose I plus 1 for I from 0 to n minus 1. Okay. So how is this special? I mean, these two formulas look almost identical, right? Except for some indices. But yeah, so first of all, can you remind me? So remember what happens if I take the sum of all entries of the h vector? What do I get? I mean, I'm not asking you to compute the sum of these coefficients. I'm saying in general, for a general polytope, what's the h vector? F sub d. f sub d minus 1. Okay, that's f sub, it's number of facets of, okay. What is the number of facets? It's the Catalan number. Nice. All right. So what we have here is a bunch of numbers which together sum up to the Catalan number. And they're all non-negative, and they form a palindromic sequence. They must be some special numbers, right? And it turns out that, yeah, maybe I should try an example. For n equals to 3, what's the formula? hi is 1 over 3 times 3 choose I times 3 choose I plus 1. So h0 is, you can just tell me the h numbers. h0 is 1, h1 is 3, and h2 is 1 again. All right, so it's indeed symmetric, and they sum up to 5. So how is 1, yeah, like 5 is the number of triangulations, so we should split triangulations into 3 groups counted like this. So the question is, what are these numbers? Anybody want to guess? Based on degree and some special vertex. No, but wouldn't you get different? Yeah, so let's say yeah, it doesn't work. All right. Any other? I mean, you can try to think of different functions on triangulations and try to probably some of them is going to work for the pentagon, or maybe for the hexagon is going to fail. It's a tricky problem. But so last time we did the associahedron, and the answer was the H vectors was given by the Eulerian numbers. And these numbers also have a name. So the answer is that these are called the norian numbers. What are the norian numbers? And so for that, I need to tell you a different interpretation of the Catalan numbers, because it's going to be more natural. As you know, there's many different combinatorial objects counted by the Catalan numbers. So I'm going to choose the convenient one for me, which is going to be, so Cn is also the number of Dicke paths from 0, 0 to n, n. And what do I mean by Dicke paths? Well, you take the plane 0, 0 and n, n. So a Dicke path is these are just lattice paths which stay weakly above the diagonal. So you have the diagonal, and then you're allowed to make up steps and right steps, and you're supposed to always stay above the diagonal. I could go all the time. I can't hear you. So I can go on the yeah, right. I have to. I can touch the diagonal, but I cannot go below the diagonal. Yeah, and so it turns out that the number of such Dicke paths is the Catalan number. So for example, maybe n equals to 3. I'm counting paths from 0, 0 to 3, 3. And I can go up, 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 right, right, right. Or I can go up, up, right, right. Or I can go up, up, right, right, right. Or up, right, up, right. Or up, right, up, right, up. So I get five objects, which is good. And now the norian number, well, the entry of the corresponding H vector is the number of Dick paths with, yeah, maybe somebody can guess right now what it's going to be. How many times it turns? Yeah, that's okay. All right. So how many right turns? Yeah, that's the actual correct guess. Thank you. So this is called with I plus 1 peaks. A peak means it goes up and then right. So of course, I mean, I showed it to you for n equals to 3, but it works for arbitrary n. If you actually compute the number of such Dick paths, you're gonna see this formula. So it's yeah, number of peaks here is going to be 1, 2, 2, 2, 3. All right. So, and that's actually, so here's a nice combinatorial problem for you. Problem, which is, okay, we know that the H's are non-negative, which of course it's clear from this picture. What's the other relation for the H vectors that we know? They're symmetric. Hi is equal to H n minus 1 minus I. How do you, yeah, the problem is to show this bijectively. So find the bijection which takes Dick paths which have I plus 1 peaks, right? So maybe you have to have a bijection that sends this Dick path to this Dick path. Sort of. This sounds like a tricky problem. And you're encouraged to try it at home. Maybe it's easy, I don't know. But to me, kind of the moral here is that we have some nice facts about general polytopes, but if we specialize to nice polytopes, we get some combinatorial statements which are sort of non-trivial, interesting combinatorial statements, and interesting combinatorial numbers that we can study. So somehow, for example, polytopes tell you which formulas like this are meaningful and deserve further study. So any questions so far? No questions? All right. So realizations. Realizations of the associahedron. And yeah, so the first one is a pretty recent one, GKZ, Gelfand, Kapranov, Zilovinsky. Well, not too recent, maybe 94 or something like this. And KZ realization. But first of all, I think it's cool. And second of all, I think it's, I mean, it's going to be related to the stuff we study later, which are secondary polytopes. So it's nice to see an example of a secondary polytope. So let's say you fix an actual convex n plus 2 gon in the plane with vertices labeled 1, 2, all the way up to n plus 2. So I want an actual, maybe draw the plane, and then my polygon is going to look like this. 1, 2, 3, 4. Yeah. Maybe this is R. So I have to actually choose the coordinates of these vertices. 1, 2, 3, 4. And then let's say I have a triangulation of my polygon. Something like this. So let's say T is a triangulation. Then my goal is to associate a vector to each triangulation in some high-dimensional space. And so here is my vector. My vector is going to be V sub T is going to be a vector in dimension in R to the n plus 2. And what I'm going to do is V sub T is given by V1, V2, all the way up to V n plus 2. And Vi is the sum of all areas of triangles containing the vertex I. So if you look at this, you should be surprised. This is a super weird definition. So yeah, let me give an example. 1, 2, 3, 4, 5. Maybe these areas are A, B, and C. Then the vector, what's going to be the vector? Can somebody tell me what the coordinates of this vector? C, A plus B plus C, A plus B, B plus C. Thank you very much. Yeah, all right. So it's a, what's the dimension of the associahedron here? Okay, interesting. It's a two-dimensional polytope, but this is a five-dimensional vector. There's a very weird property, which is that V sub T is in R to the n plus 2, but the dimension of the associahedron, as we hope, is n minus 1. So there, it's like 3 more than it should have been. But on the other hand, it's a very simple definition. So yeah, the theorem is due to GKZ 94 is that okay, so if you define sigma sub R to be the convex hull of all these vectors, V sub T, T is a triangulation of R. Then sigma sub R is a realization of the associahedron. And first of all, notice that here already, this is not just one realization. You can pick any polygon you like in the plane. In principle, you're going to get different non-affinely isomorphic polytopes. But still, each of them, so it gives like infinitely many realizations. And of course, maybe, so right, so it's a good question. Like, can we show that the dimension is actually that it's contained in some nice 4-dimension 3 subspace of R to the n plus 2? And of course, so what is? Can you give me one relation between the coordinates? Okay, so relation number 1, that is true, thank you. So sum of coordinates is equal to the area of your pentagon times 3, which in this case is times n. It's subdivided for time. Is it still? It's still times 3. Okay. Each triangle contributes his area to exactly 3 vertices times 3. All right. And so there should be 2 more relations which are independent of this one. And that's an exercise. Yeah, I mean, we're going to study this later more generally. The point is that this construction works not only for polygons, but for arbitrary polytopes. If you have an arbitrary polytope, there's a certain polytope called secondary polytope whose vertices correspond to certain triangulations of your original polytope. That's a very general construction. And yeah, so maybe I should give an example. I mean, it's not going to be convincing, but let me just try n equals to 2. N equals to 2, so I have 1, 2, 3, 4. 4. So if you assume that this is an actual square, 1 by 1 square, then the coordinates are going to be 1, 1/2, 1, 1/2, and here, so the other one is going to be 1/2, 1, 1/2, and 1. As you can compute the areas. So again, not convincing, but at least we see that okay, these are 4-dimensional, but they form a line segment, which is codimension 3. So there should be 3 relations hold for each of these. Sigma r is a line segment in r to the 4. Yeah, well, it tells you can try to come up with the relations. You can check that the sum is the same, but whenever you have some linear function, you can check that at least it's the same on these 2 vertices. All right. But yeah, if I had more time, maybe I would have shown you a pentagon that's actually a pentagon in 5 dimensions, which is actually a pentagon. It's hard to draw 5 dimensions. And that's why these polytopes are hard to come up with. Like you have the associahedron, maybe you come up with some formula for the vertices. How do you check? It takes a while to check that the result is the actual correct polytope, because each time you have to compute all these faces, right? You have to pick all these support vectors, and it's a lot of work. So let me tell you, I have 5 minutes. Let me tell you another one, which is something we've seen before, Minkowski sum realization, which is very recent, actually 12 years ago. So let's say I have some set I, a subset of bracket n, then let me define the corresponding simplex, delta sub I, to be the convex hull of the corresponding basis vectors. So I have a simplex with n vertices, and then I'm choosing a subset of vertices and taking the corresponding face of the simplex. These are going to be my objects. And the theorem, which is due to Postnikov in 2009, this is so-called low-day realization, but in a different language. But anyways, the theorem is due to Postnikov. And the claim is that if you take the Minkowski sum over I and j between 1 and n, I less than j, of the corresponding faces of the simplex. So I'm taking all intervals, basically. Then what I get is combinatorially equivalent to the associahedron. Yeah, I should say, yeah, each polytope I get is going to hopefully be combinatorially equivalent to the associahedron. So, and the weird thing about this result is it's so recent. It's super simple and it's Minkowski sums, nothing really fancy. Turns out to be the associahedron. Maybe let me give you an example. So let's say I take n equals to 3. So I should take the simplex with n vertices, which is what? Triangle. Okay, I take the triangle, the vertices labeled 1, 2, 3, and then I take the Minkowski sum of its faces, but not all faces, some of the faces. Okay, so which ones do I get? First of all, when I equals to j, this is a single point, so I can ignore that. So I take 1, 2 plus 2, 3 plus 1, 2, 3. These are the 3 summons in this. All right, so do I get a pentagon or not? Let's see. So I have 1, 2, 3, and then I add, let's say, this line segment to it. So it's going to look like this. Okay. And then I add this line segment. I'm going to get a very weird looking pentagon, but it's a pentagon. So that's the associahedron. And it works in arbitrary dimensions. And yeah, actually, I mean, from this picture, it's not too hard to actually find all the faces and make sure that the face lattice is what you get. And next time we're going to actually discuss, I'm going to actually prove it next time. And I'm going to prove it more generally. So there are these objects called graph associahedra. So you can basically run the same construction for an arbitrary graph and get some nice generalization of the associahedron. So that's what we're going to do next time. And I'll see you all on Monday. Have a nice weekend, everybody.